Okay, so this is a set of notes on integration, which are a bit more compact than the Elm, so I thought I'd use these. Well, it's called integration, the notes, but actually what we're doing in it is differential equations. So we're starting on section 2. I'll upload the whole lot, but the stuff that you actually need that we haven't done already in class is from page 38 onwards. Okay, so differential equations. It's a little bit, that's an example for electronics there, so electronic people can read that later. Right, terminology, so I'm going to start on page 39. Okay, the order of a differential equation is the order of its highest derivative. Okay, and the degree of a differential equation is the degree to which the highest derivative is raised. Okay, so the order, let's get this order, let's do a different colour for each one. Order is the order of the highest derivative. And then a different colour for this next one, pink. And the degree is the degree to which the highest derivative is raised. Okay, so a linear differential equation is one in which the dependent variable and all its derivatives only occur to the first power. Okay, so that means they're not squared or cubed, just raised to the power 1. So this first example here, we've got d2y by dx squared plus dy by dx is x. Okay, so first of all, we've got to think about the highest derivative is 2, because of this here. The highest derivative is 2. And then the power that this is raised to, it's not squared, it's by itself, so it's d2y by dx squared, but it's not squared as in the next example, which we would see in a minute look like that squared there, or that one example there. So what we can say, the degree of d2y by dx squared is 1. So we say the first one, its order is 2, second order, degree 1. Second order, because it's got second derivatives in there, degree 1, because the second derivatives are not squared or cubed, they're just what they are. Okay, so the next one, the highest derivative is 1, because it's dx by dt, and the degree of dx by dt is actually 2. Okay, so it's first order, degree 2. Okay, this first example here, this one is linear because it's degree 1. This is non-linear because it's degree 2. Does that make sense? Oh, you'll have to email me if it doesn't. Right, next one, highest derivative is 2, because we've got d2y by dx squared, 2, so that's for that bit in there. And the degree of the d2y by dx squared is also 2, but it is there, looks nice with an is there. Okay, and that bit there, that's that one. So even though there's a 3 in this other, this dy by dx, that doesn't count for anything because it's the highest one and the power of the highest one. So the highest derivative there, dx dt, and the power is 2. Okay, so it's second order, degree 2. So you've got to look for the highest derivative, that gives you the order, and then see what power it's raised to, and that gives you the degree. Okay, so let's finish that section. Next section is solution of a differential equation. The solution of a differential equation is a relationship between the dependent and independent variables. The dependent is usually y and independent is usually x, but it could be x and t. So that's just an example, that's the most common one, because y depends on x. And the dependent, if we've got dy by dx, that one's dependent on the top and independent on the bottom, x. Okay, so the solution of a DE is a relationship between the dependent and independent variables such that the differential equation, DE is short for differential equation, is satisfied for all values of the independent variable over a specified domain. Okay, become simpler with examples. The next one is, it says a simple first order linear degree. So first order, that's because it's dy by dx. Linear because it's raised to the power 1. And it's simple because you haven't got much going on there. It's dy by dx is equals to y. Now the way that we do these is dy by dx is y. Okay. So they say from experience we know that y is e to the power x satisfies this equation, hence its solution. I'll just go into that in a bit more detail here. We've got y is e to the x. If you differentiate e to the x, it's e to the x. So dy by dx does equals y. And that's a differential equation. Okay. It's also true that y equals c e to the power x satisfies the equation. Y is c e to the power x. If we've got that extra constant, it still just stays in the derivative as c e to the power x. So again, dy by dx is y. So I've done that one. Let's just mark off the colours. We've got that bit done. Thought about that bit. So this y is c times e to the power x is the general solution. The general solution, that's because it's got that the constant c in it. Now if we want to evaluate the c, we need some boundary conditions. So we're quite often told, say when x is 0, no, it's got one here actually, if y equals 4 when x is 0, so that there'll be a specific c that makes y equals to 4 when x equals 0. So if we say y is c e to the power x, and then if we substitute y is 4, x is 0, so if we say 4 is c times 1, so c is 4, as I've got there. So you've got y equals 4 e to the power x. Now that one is called the particular solution because it's particular to those particular boundary conditions. Okay, next one. Consider the differential equation dy by dx is ky. From experience, again, we know that y equals e to the power of k times x is the solution of this differential equation. And the general solution, we can put the c in front of the e. Because if we've got y is c e to the kx, dy by dx is c k e to the kx, which is k times c e to the kx, which is k times y. Okay, so that's the answer, and that's the proof there. Okay. So the next section now, what we're going to do is second order linear differential equations. So these are the ones that we've done already. Dy by dx minus ky equals 0. That's the previous one. Has a general solution y equals c e to the kx, and an in particular solution y equals e to the kx. Okay, that's just what we've done in the previous section. It turns out that y equals e to the kx is also a solution of second and higher order differential equations. So it says consider d2y by dx squared minus 6dy by dx plus 8y equals 0. Assume it has a solution y equals e to the kx. Okay, so I'm going to go ignore this here. We've got y is e to the kx. dy by dx is k e to the kx. And d2y by dx squared is k squared e to the kx. Okay, if we substitute all these into the original, all those go into the original, we've got k squared e to the kx. Here look, so d2y by dx squared is k squared e to the kx, so that goes there. So we've got minus 6dy by dx, minus 6k e to the kx, because dy by dx is k to the kx. And then we've got plus 8y, so we've got to do plus 8 e to the kx. Plus 8 e to the kx equals 0. Okay, now e to the kx is never equals to 0, so we can divide through by e to the power kx. We get k squared minus 6k plus 8 equals 0. So we can solve this quadratic because it's k minus 4, k minus 2 is 0. So we end up with k is 4, or k is 2. Two solutions. And so moving on, I'll just go over to this bit here. So we've got k, so we've got y is e to the 4x and y is e to the power 2x, are both solutions. But like before, we can actually say it's y equals a e to the 4x and y equals b e to the 2x are the two solutions. General solution. So what we can actually say, we can say if d2y by dx squared minus 6dy by dx plus 8y equals 0, y is a e to the 4x plus b e to the 2x. Okay, so that I've done it there. Let's talk through what the notes give us as well, just to make sure it all makes sense. So assume it as a solution y equals e to the kx, that's what I've done there. Differentiated second derivative and substituted it in, which is what I had there. Okay. So if y equals e to the kx is a solution, there, up to here on this one now, k squared times e to the kx minus 6k e to the kx plus 8 e to the kx is 0. So we divide through by e to the kx, and then we factorise, and you get k is 4 or k is 2. So we've got k is 4 is k is 2, and the general solution, y equals a e to the 2x plus b e to the 4x. So the key to solving these is, well, the shortcut. If you've got d2y by dx squared, this is going to be the shortcut way, minus 6dy by dx plus 8y equals 0. You can straight away say that's the differential equation. You can say k squared minus 6k plus 8 equals 0. So it's k minus 4, k minus 2 is 0. And these are, so we've got k equals 4, k equals 2. So the solution is y a e to the 4x plus b e to the 2x. Okay. Yeah. So you can do it in 1, 2, 3, 4, 5 lines. Okay. So hopefully that makes sense. I think it will. Yeah. So if you make these, say for an exam question, if you look in the past papers or if you find some online or something, you'll always see that this can make a nice quadratic that can be solved. And then the solutions are the powers of, well, it's the multiple of x in e to the kx. And you put them together like that. Okay, the next one. In homogeneous differential equations. Okay, so homogeneous differential equations are where every term includes a dependent variable y or one of its derivatives. So here, d2y by dx squared, that's got a y, derivative of y. 5 dy by dx, it's got a derivative. 6y, it's got the y, so that one's homogeneous. Okay, this one is not homogeneous, and that's because we've got 12x and 28 on the right hand side. Okay, so to solve them when they look like that, what we've got to do is we've got to find, well, we can solve if it's equals to 0 with a method that we've just outlined with the e to the kx's and the quadratic, which we can do there, and I'll talk through that in a minute. And then because we've got a polynomial on the right hand side, we substitute a polynomial on the left hand side, and you do like a simultaneous equation way, or comparing coefficients to work out the finer details of the polynomial. I'll come on to that in a minute. Okay, so there's quite a lot there. I'll just talk it through anyway. So we start off with this one. Do this bit here. So this is what we've got to solve. So we start with d2y by dx squared plus 5 dy by dx plus 6y is 0. So that's a k squared, that's 5k, and that's 6 is 0. So it's k plus 2, k plus 3 is 0. So k is minus 2, k is minus 3. And you get y is a e. They've put minus 3 first, so I'll put that one first. Doesn't matter which order you put them in there. Plus b e to the minus 2x, like so. And that's called the complementary function, okay, because that's always going to happen, because that's going to be 0. Now, we need the particular integral. The particular integral is going to be, whoops, that first bit's the complementary function. Now we want the particular integral, and that's the function that when you substitute it into the left-hand side gives the right-hand side. Okay, now because we've got a linear 12x plus 28 on the right, what we've got to do is put in a cx plus d basically, because it's not necessarily going to be a 12 or a 28, but we've got to figure out what the c and the d is. Okay, so you put in a polynomial of the same degree as what's on your right-hand side. So we've got, so we're going to say y is cx plus d, y dashed is c, y double dashed is 0. Okay, so our differential equation, which is d2y by dx squared plus 5 dy dx plus 6y is 12x plus 28. d2y by dx squared is 0. 5 dy by dx, that's 5y dashed, which is c. And 6 of the original y is 6cx plus 6d. And that's got to be equals to 12x plus 28. Okay, so that y double dashed, 0, 5 dy by dx, 5c, 6y, 6cx plus 6d. And that side's there. I haven't done anything with that yet. So don't need to write 0. So if we look at the x's, that's orders of x. 6c on the left is 12 on the right. They can be coloured in. Okay, that one there is going to be that one there because they're the x's. And then the 5c plus the 6d makes 28, but we'll come to that bit in a minute. So this means that c is 2. And then the constants, the ones without the x's, 5c plus 6d equals 28. We've just worked out that c is 2, so 10 plus 6d is 28. So 6d is 18, so d is 3. Okay, so we end up here, y is 2x plus 3. That's called the particular integral, because when you substitute that into the left-hand side, you get the right-hand side, 12x plus 28. Okay, so on this page, I've done some of this here, look there. Combine it all together in the end log. Okay, so they've ended up with y equals 2x plus 3 is the particular integral. We also had ae to the minus 3x here log. There we are. That one, that's the complementary function. And that one there, that's the particular integral. So the overall general solution is the complementary function a e to the minus 3x plus b e to the minus 2x plus the particular integral 2x plus 3. And that's the answer. So it's the sum of the two. Right, so a little bit more information about the particular integral. So I'm here. The particular integral is always of the same form as the inhomogeneous component of the differential equation. Okay, so if you've got a polynomial of degree n on the right hand side, use a polynomial of degree n to substitute in to see what the and work out what the coefficients are. If you've got sine or cosine, you've got to use a cos x plus b sine x, and you've got to use both because one differentiates to the other. Or if you've got sine kx or cos kx, again a cos kx plus b sine kx. If you've got e to the kx, you've got to use a e to the kx. And if you've got a mixture of 2 or 3 of them, you've got to use all the ones that you've got. An example. Let me do this on another page, I think, plus a page after. So it's d2y by dx squared plus 5 dy by dx plus 6y equals 12x plus 28 plus cos x is 10 cos x. I've already done some of this already, but I'll do it from the start. So we start with a complementary function. So this is a recap because I've already done this once. It's how I would say it in an exam. Complementary function first of all, k squared for that one, plus 5k plus 6.
I don't know that one.
Alexa, be quiet. Video. I'll just turn this off somehow. Right. My Alexa heard me talking to you. That one's naught. So we're going to have k plus 2, k plus 3. Factorise the quadratic or use the formula. Is naught. So k is minus 2, k is minus 3. So the complementary function, and you can write that as cf, y, sometimes it's written y cf like that, a e to the minus 3x plus b e to the minus 2x. Okay, and that's an underline. I forget about that, we've done that for now. Then we've got to do the particular integral. Next, particular integral. So on the right here, we've got a polynomial 12x plus 28, and then we've got 10 cos x. So for that one, we need to try y, particular integral if you like, is cx plus d plus e cos x plus f sin x. So when it's a cosine, you've got to put both in. Okay, I'll just put y because it's going to get messy otherwise, but just remember that's not the whole y, it's just the particular integral part of y. So we're going to substitute this into the equation. So the y is there, look, I can multiply it by 6, that's fine. I've got to do 5 dy by dx, and then the second derivative as well. So I need y dashed next, so that's going to be c. Cosine differentiates to minus sine. and sine differentiates to cosine. And we need the second derivative as well to go in there. Y double dashed, well that's 0 at that point. That one's a 0 there, so I don't need to write them down. Got sine to cosine to minus sine to minus cosine, and then back to sine again. So this is minus sine, so it's going to be minus e cosine x, and cosine goes to minus sine, so it's minus f sine x. So I've just differentiated the row above. Substitute it all in. Substitute it all in. I'll just rewrite it again here. d2y by dx squared plus 5 dy by dx plus 6y. It's got to be 12x plus 28 plus 10 cos x. So we've got minus e cos x minus f sine x. That one, that's the d2y by dx squared there. Okay. And then we've got to do plus 5 dy by dx. So I'll give this one another colour. Let's do that one this colour. Y thingy, y dash dy by dx is going to be there. So we need 5 of these, 5 of that one. So it's plus 5c minus 5e sine x. Look, all these have to be multiplied by 5. So it's 5c minus 5e sine x, so that's going to be under there, minus 5e sine x. And then the last one here is going to be plus 5s cos x, because it's y dashed times 5 there, 5f cos x. So it's plus 5f cos x. That's that one done. And let's do another one. The last one we need is 6 y's, so it's 6 of these. So it's 6. 6 is in front of all these and put into the right places here. So we've got 6 plus 6cx, which is that one, plus 6d, plus 6e cos x, there, plus 6f sine x. Yeah, let's just check I got all of these right. Minus, that's the d2, that's the y double dash line. This is 5y dashed across there. Yep, that's right. And this is 6 y's along there. Just quick check. Yeah. And all that has to be equals to 12x plus 28 plus 10 cos x. And we don't want any sine x's. Okay, so when we add all these together, we need 10 cos x's, no sine x's, 28 and 12x. Okay, right, this one looks quite useful to start with. Let's go for a peachy colour. That one and that one. That's straight away, looking at those two, we can say that's the powers of the, that's going to give us C is 2. Okay, which is good. Okay, and then we can move on to the next one along. Let's go for this one. C is 2, so that's 10. 10 plus 6d is 28. I've already done these ones actually. 10 plus 6d is 28, so therefore d is 3. Because 10 plus 6 times 3 is 28. And the next one, we've already done that one anyway, so I need to think about the sines and cosines now. So I'm going to look at the sines now. I've got 5f, because I've got let's look at these. Let's go for here. Right, minus f plus 6f is 5f, minus 5e is 0. So what have we got there? 5, so this is from the order of the sine x. We've got 5f minus 5e equals 0. So if we add 5e to each side and divide by 5, we end up with e equals f. Okay, I've just did that, yep, just to save a bit of space. So now let's look at the cos x's. That one should be not there. That one should be coloured in there. This is where they all come from. And the next one along here, minus e plus 6e, so that's 5e plus 5f is 10. 5e plus 5f is 10. But e is equals to f. So therefore we can say 5e plus 5e is 10. So if 10e is 10, e is 1, and f is 1 as well. So we have an answer. We've got, it's just such a shame I've run out of paper there. But we've got an answer. Go to the top for the answer. Answer. Oh, I wish I'd started. Oh, never mind. Find answer after all the working. After all the work below is, so we've got cx, so it's y is cx, which was 2, plus d, and d is 3, e cos x, well e is 1, so it's plus 1 cos x, and then f is 1 as well, plus 1 sin x. Okay, so there you go. So it's just being careful and substituting in nicely. Oh, that's the particular integral. I'm going to put it on the next page just to. I'm going to run out of room again. So let's just go on to the next page. Let's add a new page in there. Right, so hence the particular integral is it was 2x plus 3 plus cos x plus sin x. So that's the particular integral. But you actually want the final solution. Y is the particular integral plus the complementary function. So y is a e to the minus 3x plus b e to the minus 2x plus 2x plus 3 plus cos x plus sin x. Yes, so there you go. Yeah, we always have one of these in the exam, but not quite as complicated as that. Right, so look, so that takes us up to there, which comprises a complementary function, particular integral 1, particular integral 2. So they've broken this down. That's be their particular integral 1, particular integral 2. But I just did it all in one go, which, you know, have a look at their solution as well. Okay, so that's one type of differential equation that you need to solve. The next ones that you're going to need, I'll keep going, because if I can do this in one go, it'll be so handy for you people to just have, and me, so it's just a lot less complicated. Differential equations 2. Where we're at next, we've got it's separation of variables, which does come up at level 3. And I know because I've been doing some level 3 videos today as well. I've already done this once for them, but I'll have to do it again for you. Right, so you should have seen these before. Full solution. But if you haven't, or if it's been a while, on next 2 pages. Right, so there's that. Okay, so what they've got there, dy by dx is f of x. Right, we've got dy by dx is f of x. Okay, so what you would do here, if you integrate both sides with respect to x, dy by dx, integral of f of x, dx, and you can think of these cancelling. Integral of dy by dx is going to be bring it back to y, because this is saying differentiate then integrate, so it's y. Integral of f of x dx, which is that there. But more generally, you would have dy by dx is a function of x times a function of y. So what we do is we collect the y's to the left here, and then we integrate both sides with respect to x. So you end up with the integral of 1 over g of y dy, because if we differentiate and then integrate, that becomes dy. Integrate this side with respect to x, it's f of x dx. So this may give y in terms of x. Okay, I think I've got enough room down there to do this one actually. Example. Right, so example 39 is, so we've got dy by dx is 3x squared e to the minus y, and that y, and we've got y of 0 is 1. Okay, so because we've got the y's on the top there, we need those y's to collect with those y's over there. Then we integrate both sides with respect to x. So I'm going to multiply both sides by e to the plus y, because that will cancel out that e to the minus y. Then I'll integrate both sides with respect to x. So it has the effect of cancelling out that one there. Not really, but I shouldn't really say that, but it's what happens. And then we can integrate both sides. So the integral of e to the y, e to the y. The integral of 3x squared is x cubed. We put plus c. And we've got an e on the left. We would really like to have a y there. So we do ln of the right. Okay. And then to find the c, we substitute the initial condition there, which is that when x is 0, y is 1. So 1 is ln of 0 cubed plus c. And so 1 is ln of c. So therefore c e to the power 1, because it's got ln on the right, so it's e to the power 1 on the right. And you end up with y is ln x cubed plus, instead of c, we can say e. Does that make sense? Just a little read over that, make sure it's all quite straightforward. Let's go. I'll just talk over this example again. So what I did first of all, put that one, multiply both sides by e to the y to get like that. And then I've integrated both sides with respect to x. So it becomes dy only there, dx only there. The integral of e to the y on the left there is e to the y. And the integral of x cubed, of 3x squared, sorry, is x cubed. We put plus c. We've got e to the y on the left, and we really want just y, so we take ln of the right from there. So y is ln there. And then so that's one bit done. That's the question. This is what I wanted to do, put some lines in. Then we substitute x is 0 and y is 1, and this is to find the c. So on the left hand side we've got 1, on the right hand side we've got ln of 0 cubed plus c, because x is 0. So 1 is ln c. So because we've got a ln there and we want c, we take e of the e, raise the other side, make the power, the other side the power for e and its c is e to the power 1, and then rewrite the original back with, that should be blue, back with there, y is ln x cubed plus e. Okay, right, the next one, EG40, hopefully I can fit it in down this side here. I'll make this a bit smaller, I wonder. Oh, that might be EG40 down this side here. So dx dt now is t squared plus 1 over x squared plus 1. So the first thing to notice, so x squared plus 1, x is on the top, so those x squareds plus 1 up there with them, and then we're going to integrate both sides with respect to t. So let's put these in brackets. Multiply both sides by x squared plus 1 then, that's to get the x's onto the left, which dx, and that's going to leave t squared plus 1 on the right. Then integrate both sides with respect to t. So that's going to cancel out. It would be dx dt there, but we're integrating with respect to t. So it's just like that. Then we do our add 1 to the power, divide by the new power. 1 integrates to x. T, add 1 to the power, divide by the new power. 1 integrates to t, and plus c. And that's it. Yeah, so I didn't need a new page for that one after all. Okay. Right. Okay, now remember this example. This is an electronical engineering one. So if you do that, you can read this. I'm not going to do this one today because it's I've done it before in the past, and I'm certain it's right. But you can read that through, but it's only for electrical engineers. So it might come in next year, you might need it. So it'll be useful then. Okay. And that completes that method. So, just see how many pages I've got of this. It's page 49, and I've got to get to page 58. I'm going to do it. Right. Okay, this next method. Use of integrating factor. Okay, first order DEs. Right, so you don't need to learn this first bit, but let's just talk it through. If we've got, this method, the integrating factor method, is used when we need to solve differential equations. You've got the dy by dx there, a function of x times y there, and a function of x on that side. Okay, now what we need to do, and I'll show you how to find the integrating factor soon, but the idea is, once you've got this integrating factor, look, you multiply everything by this integrating factor. So dy by dx, the p of x y becomes multiplied by mu of x, and so does that there. Okay, so once we've got this, and the reason we've done this is because we're going to make this the left hand side, that's two things multiplied together, and it's going to be, that's the result of using a product rule, because when you do the product rule you end up with two things added together. And if you actually so we've done this here, look, because if you differentiate mu of x times y, it's the product rule. If we differentiate mu of x times y, so it's our first times the derivative of the second plus our second times the derivative of the first. Okay, so that bit there is actually there. So this bit here is here. So if we've got if we forget about the y, we've actually got that mu dashed x is mu of x y. Mu of x times y. No, that's not quite right, sorry. Mu, that one's in there. We've actually got gone on to the next one. Oh, they're doing the product all over that side, that's why. Okay, so right, so the left-hand side is mu of x dy by dx plus y mu dashed of x. Okay, we'll come back to that on the next page. Right, that's going to be a c over what happens, how that lot links to that lot on the next page. But if we can write this product rule here, once we've worked out what mu is, and it's all linking up here that the p of what? P of x. Look, mu of x times p of x has to be mu dashed. Mu of x, p of x has to be this mu dash because the y is the same there and there. But we're going to do that on the next page. But if we can say that this is equals to this, okay, if a function exists, then if we integrate this mu of xy, it's going to be the integral of all this. Well, it's the integral of this side actually. Integral of, this is d by dx of the multiplying factor times y. So multiplying factor times y is the integral of this one here. Okay, and then y is 1 over mu x times the integral of the right hand side. But we need to find the mu. So this method only works if there exists a function mu such that d by dx mu xy is mu x. I think I had that on the other side there. D by dx mu x times y. I'm going to write this bit down there now. D by dx of mu x times y has to be equals to mu x dy by dx. So this is first times derivative of second plus second times the derivative of the first. And that has to be equals to mu x dy by dx. And where this is come from is here, plus mu x p of xy plus mu x p of xy. Okay, so when you look, that's the same. So what you actually end up with, mu of x p of x there has to be d by dx mu dashed. And that's what I was getting to there. That bit there has to be, well, you cancel out the y. So mu dashed of x is mu of x p of x. Mu dashed there, mu of x p of x. Okay, so by separating variables, so we've got we're going to have the integral of p of x dx equals the integral of 1 over mu x dx. Okay, because we're going to put that one down there and then integrate both sides with respect to x. So the integral of px, yeah, So the integral of px dx, you don't ever have to remember this, is log mu x, and we ignore the plus c. So you actually end up with mu x is e to the integral of px dx. It's a lot easier in practice. Right, so you don't ever have to remember that. That's just an explanation of where all that comes from. Here, right, so what we've got to do, we've got dy by dx plus y of x equals 1. Okay, if you remember, our p of x is this, the coefficient there is 1, and that's important. And then p of x, the integrating factor that we end up with is the exponential of the integral of px dx. And that's what we've ended up there, look. So coefficient 1, tick. With p of x here is 1 over x, because it's everything apart from the y in this second one here. So mu is the exponential of the integral of 1 over x dx. That's the integrating factor. Every time is the exponential of the integral of the function of x that's multiplying the y once you've got coefficient equals 1. So this is the exponential of log x, which is actually x. Okay, so what you do next is you can say, if we multiply everything by mu, x dy by dx plus y equals x. And this is the method. So step 1 of the method is get the integrating factor, which is the x, or step 1 actually is make sure you've got a 1 there, which we have. Step 2 is the integrating factor is mu, is the exponential of the integral of the function of y, a function of x that's multiplying y. So it's x there. The next step is to multiply through the original equation by x. So it's x dy by dx plus y equals x. Now this is the product rule idea. This is d by dx of xy equals x. So what's happened there? Look, first times the derivative of the second is x dy by dx plus second times the derivative of the first, so that's y times 1, which is y. So we have d by dx of xy is equals to x. Integrate both sides with respect to x, so xy is x squared over 2 plus c, and then divide through by x. Y is x over 2 plus c over x. Okay. And then if you was given any conditions, which we haven't been, we could work out what the c is, but we haven't been. So we'll move on. So the next one, again, I'll fit these in down here, I think, down this side here. That's handy to have. So example 43. T dx by dt plus 3x equals e to the t over t squared. The first thing we do here, coefficient of this first one has to be 1, so we've got to divide all the terms by t. So dx by dt plus 3x over t e to the t over t cubed. Then we find so that's step 1, divide by t. Step 2, find the integrating factor. And it's the exponential of the integral of 3 over t. The previous example, it was dy's by dx's. But this one, it's dx by dt, so it's the multiple. It's the function of t that's multiplying the x there. So dt, so it's the exponential. This is 3 ln t. So it's the exponential of ln t cubed, which is t cubed. So step 3 is multiply every term in 1 by t cubed. So in star, multiply star by t cubed. So it's t cubed dx dt plus t cubed times 3x over t equals e to the t. And then we're dividing by t cubed and multiplying by t cubed, so that's going to cancel out. And that's going to cancel down to a 2. So what you actually have now is the product rule, the answer of the product rule on the left, and that is the product rule applied to d by dt of x t cubed, and that's just straightforward e to the t. So if we look here, first times the derivative of the second, so it's x times 3t squared, x times 3t squared there, plus second times the derivative of the first, well that's there, look, t cubed dx dt. And then we go on to integrate. So this is step 4, finish it off if you like. So we can say xt cubed is the integral of e to the t dt, which we know is e to the t. And we want x, so x is e to the t divided by, plus c, all divided by t cubed. That's another one done. e.g. 44. Got dy by dx plus y is 2x plus 5. Okay. Coefficient of dy dx is 1, so we've done step 1. So we go straight into step 2. Integrating factor, the exponential of the integral, and it's 1 this time, because if you look, the y is what we're interested in, is the multiple of the function of x that's multiplying the y. Well, that's just 1 dx, because that's e to the x. 3, multiply everything by e to the x. Okay, and see that this is a product rule. Y e to the x. Quick check. First times derivative of second is that one. Second times derivative first is that one there. Yeah, so we're okay. E to the x, 2x plus 5. Okay. And then we've got to integrate. Step 4, we've got integrating. So y e to the x is the integral e to the x, 2x plus 5 dx. Okay, so we've got to do integration by parts on here. So we've got e and a. So if you remember, our u is going to be our algebra, 2x plus 5, which will differentiate to 2, which differentiates to 0. So our v dashed is e to the x. So we've got to integrate these right up to that 0. So it's that one times that one minus that one times that one. Okay, so we have y e to the x is 2x plus 5 e to the x minus 2 e to the x plus c. So it's 2x plus 3 e to the x, because that 5 and that 2. 5 minus 2 is 3 plus c. So y is divided both sides by e to the power x, 2x plus 3 plus c over e to the power x. That's example 44. Okay, what we've got example 45, 46. I think they repeat themselves at the end actually. Just have a little look through and see where we're going with these. 48, 49, example 47, Yeah, so 45, 46, so 48, 49. More integrating factor. Okay, maybe this one will be all right with the writing that it's got already. So example 45, solve tan x divided by dx plus y equals sec x, which we know is 1 over cos x. If you remember that third letter C, and a C there. So the first thing we've got to do, we've got to make the coefficient of this equals to 1. So we've got to divide everything by tan x. So it's dy by dx plus 1 over tan x times y equals sec x divided by tan x. So dy by dx, next line now. So I've done that line. I'm happy with that line. So the next line, dy by dx, 1 over tan x is the reciprocal of tan x. So it's cos x over sin x times y. Sec x on the top there, sec x there is 1 over cos x. And dividing by tan x, that's multiplying by cos x over sin x. Okay, the integrating factor is the exponential of the integral of this one here, which is a function of x, which multiplies y. And then that's e to the log sin x. Remember the integral of cos x over sin x dx. It's log sin x. Because if you differentiate this, it's 1 over sin x times the derivative of sin x, which is cos x. And then, so it's log sin x, and then the e and the log, you can think of them as cancelling out, so it's sin x. So then we multiply through this one by sin x. So we get sin x dy by dx plus cos x times y equals, they've already cancelled. We've got 1 over sin x multiplied by sin x is 1. And then this side is always d by dx. It's always integrating factor times y. So if you do a trick, look, first times the derivative of the second is that 1. Second times the derivative of the first is that 1. Integrate both sides with respect to x. Sin xy is the integral of 1 dx, which is x plus c. And then we can rearrange to divide both sides by sin x. Y equals x plus c over sin x. Number 46. 1. Let's look how far does that one go. Oh, look at all that there. Right. If I can make that a bit shorter. I'm going to try and get that one a bit shorter down here. I don't want to read that because that looks a bit too much. So, example 46. We've got, first of all, make coefficient of dy by dx equals 1. So we're going to have dy by dx plus 3x over 1 plus x squared y equals 5x over 1 plus x squared. And it says y equals 2 when x equals 1, which is great. So that means we're going to work out what the constant of integration is at the end. So we've done step 1, make the coefficient of dy by dx equals to 1. Step 2, integrating factor is the exponential of the integral 3x over 1 plus x squared dx. So it's the exponential. Now we've got a fraction with almost the derivative of the bottom on the top. That's it. It's going to be log of 1 plus x squared. If we differentiate log of 1 plus x squared, it's 1 over 1 plus x squared times 2x. But we actually want 3x. So we've got to multiply it by 1.5 there. So it's the exponential of the log of 1 plus x squared, so 1.5, which is actually 1 plus x squared, so the 1.5. Okay, so that's step 2 done. Step 3, multiply throughout by the integrating factor. 1 plus x squared to the 1.5 dy by dx plus 3x. Now I've got 1 plus x squared to the 1.5 going in the top there, but I've got divide by 1 plus x to the 1, so it's going to leave a 0.5 there. Y equals 5x, and similarly there I've got a 1 plus x squared to the power 1 in the denominator there, so that's going to be 1 plus x squared to the 0.5, and they cancel out. So, before I get into that actually, this is d by dx of y times 1 plus x squared to the power 1.5 equals 5x, 1 plus x squared to the 0.5. Okay, so integrate both sides with respect to x. Y 1 plus x squared to the 1.5 is 5 times the integral of x, 1 plus x squared to the square root is a half. I'm going to put it like that. Okay, so that second side, the right hand side, needs that integral there, needs solving by substitution. So if we let u is 1 plus x squared, du dx is 2x. So we can say x dx is a half du, rearranging that. So we end up with y 1 plus x squared to the 1.5, 5 times the integral, a half, u to the half du. Just talk where that comes from. X dx is a half du, which is that bit and that bit. That's a u square root u to the half. So therefore y 1 plus x squared to the 1.5 is 5 over 2, add 1 to the power, divide by the new power, plus c. That 2 will cancel with that 2. So y 1 plus x squared to the power 1.5 is 5 over 3, 1 plus x squared to the 1.5 plus c. Actually, it starts to look a little bit nicer. I'm going to divide both sides by 1 plus x squared to the 1.5. So y is 5/3 plus c over 1 plus x squared to 1.5. Answer. Which is there, look. Y 5/3, c 1 plus x squared to the minus 3 over 2. So my writing there takes us up to there on that side. Okay, so you can read through theirs or you can read through mine by the side. I don't mind, obviously. Right, now we can find the c with this one. So we can substitute. I've ended up with y equals 5/3 plus c over 1 plus x squared to the 1.5. And we can substitute x is 1, y is 2. So 2 is 5/3 c. 1 plus 1 is 2 to the 1.5. 1 plus 1, 1 squared is 1. Take 2 is 6/3 minus 5/3 times 2 to the power 1.5 equals c. So I've taken the 5/3 off each side and multiplied by 2 to the power 1.5. So c, 2 to the 1.5 times 1/3. Okay. Right, 2 to the 1.5 is 2 times root 2, because the 1 is that 2 there. 2 to the 1 is the 2, 2 to the 0.5 is root 2. And then the multiply by 1/3 is the same as divide by 3, which is, look, we're up to there in this one. That's there. Okay, and that's right there. So we can end up with y is substituting. So basically that c is going back into there. 5/3 plus 2 root 2 over 3, 1 plus x squared, so 1.5. Okay, now that's the answer. Now I feel like they talk about integrating factor again in these notes. So I'm just going to jump forward to the exercises because there's nothing new there. We've done all that already. So I'm just going to jump through to example. I'm going to do all the examples. You can read that, but I feel like it's quite repetitive. So I don't feel like I need to do it. E.g. 47 is the next one. X cubed dy by dx plus y times 3x squared equals x squared. Step 1, get the coefficient of dy by dx to be equals to 1. So dy by dx is y times 3x squared. Oh, sorry, y plus, they're not equals. Divide by x cubed, x squared divided by x cubed. So that is going to cancel with that and make that a 1. That is going to cancel with that and make some 1s in there. So we have dy by dx plus 3 over xy is 1 over x. So step 2, find the integrating factor. Is the exponential of the integral of 3 over x dx, which is the exponential of 3 ln x equals theirs, which is exponential of ln x cubed, which is x cubed. So number 3, multiply everything by x cubed. And when you multiply this second one by x cubed, that x cancels one of them to make 3x squared. Multiply that by x cubed, x squared. So d by dx of x cubed y is x squared. Just ignore that bit there. I'll put it down there, put it on that side. Apply in the product rule, that says, if you want to read that back, just so it's not messing up my notes. So number 4, integrate. X cubed y is the integral of x squared dx. X cubed y, x cubed over 3 plus c. So y divide by x cubed, 1 over 3 plus c over x cubed. Okay. It's quite funny the way they've set this out. Where's the answer? Example 47. There. That's as far as they've got, and then solved. So I've just done the final bit there. So that's as far as they've got there. More reading for you. Example 48 and 49. So example 48 next. This is what you need, is some examples, and I'll go through some exam paper questions for you as well. I'll get these notes done today. So this would have been all the lectures. Yeah, so we've nearly got there, just 2 examples to go. So example 48. X dy by dx plus 4y equals 1 over x squared. Divide through by x, divide by dx plus 4 over xy, 1 over x cubed. Now, what people do is sometimes forget to divide that side, the right hand side. Even I do sometimes. I try not to, obviously. But it can happen. Anyway, step 2, integrating factor. It's the exponential of the integral of 4 over x dx. So it's the exponential of the integral of 4. Just get this right. I can do that one. I don't need to. It's the equals the exponential of 4 ln x. Exponential of ln x to the power 4, which is x to the 4. That was step 1. That's step 2. Step 3, multiply through. multiply this one through, not the original top line. The one with the coefficient of dy by dx is equal to 1. X to the 4 dy by dx plus 4x cubed, that one is, y is x. So this is d by dx, x to the 4y equals x. Okay, that's the product rule. First derivative of second plus second times the derivative of the first. Okay, and then step 4 is to integrate. So x4y, add 1 to the power, divide by the new power, plus c. Divide through by x to the power 4. So that becomes a 1, that becomes a 2. 1 over 2x squared plus c over x to the power 4. Okay. Right, last example. Example 49. X dy by dx plus 4y. I'll do this under here. X dy by dx plus 4y equals 1 over x squared. We've got x equals 2, y is 1. Right, so first step, dy by dx plus 4 over xy is 1 over x cubed. Have I just done this one? Dy by, yeah, it started on the previous page. Dy by dx plus 4 over xy is 1 over x cubed. Up there, look. So that one there, this is the same here. So our answer, we've got all the steps from the previous page. Y is here, 1 over 2x squared. This is the previous example. I'm not doing it again. 1 over 2x squared plus c over x to the power 4. So what we can do now, this is substitute x is 2 and y is 1 to work out what the c is. So we substitute that in. 1 is 1 over 2 times 2 squared plus c over 2 to the 4. So 1 is 1/8 plus c over 16. Multiply everything by 16 to get rid of this, divide by 16. So 16 is 2, because 16 times an 8 is 2, plus c, so c is 14. And we end up with y, 1 over 2x squared plus 14 over x to the power 4. And that, ladies and gentlemen, concludes the differential equations.